Hello, good evening, Ayush. So how did you do in your test? Hi Shingarika, how are you? How was your test? What happened? You people are not responding? You can hear me now? Where are the others? How many people had joined in the previous class? Okay, Raksha Bandhan. Good. Good evening, Kanishk. Chalo, then we start. I think today many people are not going to join, huh? Some of them are still celebrating Raksha Bandhan. So let's go start. Okay, so today we are going to start a new chapter. The previous we had done all numericals also. We spent quite some time in it. Okay. And now today we are going to start the next chapter, which is current electricity, which is a very important chapter, and you get questions from this chapter even in your class 12 also. Okay, in your IIT exams also you get a lot of questions from this chapter, so something to be focused on. We had done a bit of it in class 9 also. Okay, so good evening Amisha, welcome. Good evening Archika. Okay, you got your you haven't got your result. It's not auto checking now. Now I have to do the checking, so it'll take time. It has come to me. I'll do the checking and then I'll give you the marks. Now the machine is not doing the checking now this is descriptive test, so I'll be doing the corrections and then I'll give you the marks. Don't worry, it'll take some time, at least 2-3 days. Okay, I'll just download them and then I'll check them and then I'll reload them for you to see. So we start today by revising whatever we had done in class 9. Okay, in class 9 we had studied that when two non-conducting bodies are rubbed together, okay, then they acquire a charge. Why do they acquire a charge? Why do they acquire a charge? Okay, you are talking about your school test. Sorry. Okay, tell me now. Why does when two non-conducting bodies are rubbed together, they acquire a charge? Why do they acquire a charge? You also have to tell me what do I mean by charge. Okay, you also have to tell me what do we mean by charge. I'll just hide this so that once you have spoken then I bring it down. Okay, because of transfer of electrons is the correct answer which Shingarika gives. Okay, now what is charge? You have to tell me what is charge. What is charge? Good evening, Kritika. You joined very late. Tell me quickly, we move on then with the lesson. No issue. Tell me now what's charge. Now that you're late, that's your punishment. You have to quickly tell us what's charge. We studied this in class 9. I myself have taught you this in the previous class. No? Chalo, we go now. I'll tell you and then we proceed. Okay. Now what's charge? Electric charge is the physical property of matter. Charge exerts a force when, very nice, correct Shingarika. That's what I have also written. Shingarika also writes the same thing. Okay, she says that charge exerts a force when placed in electromagnetic field. Okay. Archika says it means that when a body has more or less number of electrons. Okay, both of you are correct in a way, so we'll understand this. Okay. Now, like Shingarika says, electric charge is the physical property of matter that causes us to experience a force. Okay, if the body is neutral and I place it in an electromagnetic field, it experiences no force. But on the other hand, if the body is charged and it moves through an electromagnetic field, then it will experience a force on it. Okay, so it is a property which causes the body to experience a force. It causes the body to experience a force when placed in an electromagnetic field. Okay, now Archika and Shingarika have also given us the reason. Okay, we know that all matter is made up of atoms. Okay, now the atoms have protons and the atoms have protons. Come on, the atoms have protons and neutrons inside the nucleus. Okay, and electrons are revolving round. Okay, electrons are revolving round. So what happens when we rub? Suppose I am rubbing glass. Okay, I am rubbing a glass rod, okay, on silk. This all we did be in class 9. Okay, if I rub it on a silk cloth, okay, then what happens? That some electrons from this rod jump onto the silk. Okay, now this has 4 electrons and 4 protons in this example. Got it? This has negative charge, this has positive charge. Okay, so the net charge on it is 0 or nil. It doesn't have any charge. Neutral, it's neutral. Okay, it's neutral. It doesn't have any charge on it because the number of protons is equal to the number of electrons, and the charge on an electron is exactly equal to the charge on a proton. So it nullifies algebraically. Okay, and the atom is neutral. But when some electrons have been lost, okay, then the glass rod starts attracting bits of paper towards it. Okay, so it shows that now this glass rod is positively charged. Okay, and since the electrons have jumped onto the silk cloth, so this is negatively charged. Got it? Now they say that this happens only if it is a non-conductor. Why not in case of a conductor? Do the conductors don't lose electrons? Of course, the conductors also lose electrons, but they are quickly neutralized because we are conducting. Okay, and it can be conducted from us to the conductor and it balances quickly. But whereas in case of a non-conductor, even though we are holding it in our hand, it is not able to, electrons are not transferred, and hence it continues to have this electrostatic force on itself. Got it? Till the time it stays charged. When I touch it to something and it is able to take back the electrons, then it becomes neutral once again. Okay. Similarly, when we rubbed ebonite, okay, we rubbed ebonite on fur. Okay, now this side we had fur. So I rubbed ebonite on fur and it also acquired a charge. Okay, and when I brought 2 such ebonite rods, they repelled each other. Similarly, 2 glass rods repelled each other. But when I brought this glass rod towards this ebonite rod, then they started attracting. Okay, showing that the charge on both of them are different. Okay, so we could have named them anything. We named the charge on glass rod as positive. Okay, and we named the charge on ebonite as negative. Got it? हमने नामकरण कर दिया. अब जो भी चार्ज ग्लास रॉड ऑन सिल्क से रिपेल होगा, मतलब उस पर सेम चार्ज है, तो विल से दैट बॉडी इज पॉजिटिवली चार्ज. और जो भी चार्ज एबोनाइट रब्ड ऑन फर से रिपेल होगा, ठीक है, मतलब उसके ऊपर सेम चार्ज है, So we'll say that it has negative charge. Understood? Everybody understood? Okay, we move forward now. अरे यार मेरा पेन कौन सा था? Just a minute, I'll have to move out. Something went wrong, my pen is not working, I don't know, I clicked something. It's not going away now. I clicked, but it continues, because I was changing it on the screen. Just a minute, I have some problem, it's not going away. I can't see the pens. Okay, there they are. Done. Chalo, thank you. Okay. So understood, everybody? Now it is because of the transfer of electrons. Okay. And the second thing which you must have got to see is that what will be the charge? Okay, we represent charge by a Q. Okay, charge is represented by a Q, and we have understood that it is quantized. I had told you in class 9 what do I mean by quantized. Charge is quantized. We have learned two things: like charges repel and unlike charges attract. And the third thing which we now are discussing is that charge is quantized. Okay. Archika says it was a paintbrush tool. Yeah, I clicked it accidentally and I didn't know how to move out of it. Okay, so charge is quantized means what? It means that I know that a body is getting charge because of a transfer of electron. Okay, if a body gains a few electrons, it will be negatively charged. On the other hand, if a body loses a few electrons, okay, then it will be positively charged, because as such the atom was neutral. And now it is deficient in electrons, which means the number of protons is greater. And here it has gained some electrons, it was neutral. So it has excess negative charge. So this is negatively charged. Got it? So what do we see from this? That whatever charge a body has, it will always be in multiples of the electronic charge, which means it will always be in the multiples of the charge which is there on an electron. Okay? And what is the charge on an electron? It is minus 1.6 into 10 to the power minus 19 coulombs. Okay, so here we are discussing coulomb also. The unit of charge is coulomb. We represent it by a capital C. Okay, unit of charge is coulomb. This is all we had done in class 9. Unit of charge is coulomb. We represent it by a capital C. Okay, so now let's go to find out how many electrons, okay, will make 1 coulomb charge. Okay, 1 coulomb charge is equal to Ne, okay, which means 1C is equal to N into 1.6 into 10 to the power minus 19. Got it? Which means N is equal to 1 divided by 1.6 into 10 to the power minus 19. Got it? So I transfer 10 to the power 19 on top. It was negative, so it becomes positive, divided by 1.6. Okay, I can write 1.6. I remove the decimal, so I have 10 over here. Okay, and I borrow 1 0 from there, so it becomes 100 into 10 to the power 18. Okay, so when I divide it, what do I get? I get 6.25 into 10 to the power 18. Okay, this is the number of electrons which will constitute 1 coulomb charge. We have understood that charge is quantized, which means Q is equal to Ne. Okay, so what is the number of electrons which is going to constitute 1 coulomb charge? We have divided it by the electronic charge, and we come to the conclusion that 6.25 into 10 to the power 18 coulombs 18 numbers of electrons will make 1 coulomb charge. We didn't take the sign beta because we are not interested in whether it is positive or negative. Okay, we are interested in the quantity of charge. Okay, we are interested in the magnitude of charge, because here the negative sign or the positive sign is showing whether the charge is negative or positive. So it may confuse us. Okay, and we may get a number in negative. We may get a number in negative, which is not possible. Okay, negative number of electrons will give you 1 coulomb charge. So there the sign is showing us the type of charge, and we know that we have to divide it by the magnitude only to get the number of electrons which will constitute 1 coulomb charge. Got it? Because clear? Shingarika, understood? So we now go back to your NCERT book and ensure that we have read everything, and then we come back. Okay. So we have discussed this. Okay. The transfer of electrons, the body gets charged because of the transfer of electrons that we have done. Then we have also done the body which gains electrons becomes negatively charged. The body which loses electrons becomes positively charged. Okay, then we have done that there are two kinds of charge: the positive charge, which is the similar to glass rubbed on silk, and there's negative charge, which is similar to ebonite rubbed on fur. Then we have also discussed that two like charges repel each other and two unlike charges attract. Then we have also discussed that charge is represented by Q, and then we discussed that coulomb is the SI unit of charge, which we represent by a capital C. Okay, this we didn't discuss. Okay, there are smaller units also of charge, okay, which are millicoulomb, microcoulomb and nanocoulomb. Okay, milli means 10 to the power minus 3 coulombs, micro means 10 to the power minus 6 coulombs, and nano means 10 to the power minus 9 coulombs. Okay, these are smaller units of charge. If we are measuring an extremely small charge, instead of using a coulomb, we can use millicoulomb, microcoulomb, nanocoulomb. Okay, then we also understood that charge is quantized. Okay, Q is equal to Ne. Shingarika, your question's answer is here also. You can see that Q is equal to plus or minus Ne. Okay, if the number of electrons have been lost, then the charge will be positive, and if electrons have been gained, then I'll put the negative charge. Okay, so for finding the number, I don't need this. This just tells me whether the charge is positive or negative. No issue. Welcome Dikshant. He says, I'm sorry for being late. Okay, so we move forward now. The negative sign, okay, when there is excess of electrons, then the negative sign is there, and when there is deficit of electrons, then we put the positive sign. Clear, everybody? And we have calculated this also, that 6.25 into 10 to the power 18 electrons will constitute 1 coulomb of charge. Next, we have to discuss the concept of current. Okay, so let's discuss it over here itself. We have space over here. Now, charge in flow. Okay, if water is flowing, we say water current. If wind is blowing, we say wind current. So if charge is flowing, okay, we say electric current. So this chapter is about electric current. Okay, so anything flowing is called a current. So what is flowing in case of electric current? In case of electric current is defined as the rate of flow of charge. Okay, what is the rate? Okay, rate means anything divided by the time, okay, for which it flows, which means Q by T should give me current. So how do we denote current? We denote current with a capital I. Okay, so I, what is electric current? Electric current is the rate of flow of charge. If Q charge has flown in time T, I divide Q by T, which means how much charge from that particular cross section of the conductor went by in 1 second. That gives me the current. Clear, anybody? Okay. Anything else? Okay, this we have already done. T ho gaya. Okay, now the unit. Okay, we know that the unit of charge is coulomb, and we know that the unit of time is second. SI unit is second. Okay, so what does the unit of current become? It becomes coulomb per second. Okay, so in honor of James Ampere, Andre Ampere, we have named it ampere. Okay, so we say that and we denote it by a capital A. Okay, so ampere is the unit of current and we denote it by a capital A. So 1 ampere is equal to 1 coulomb by 1 second. So how do we define it? This is the definition. Okay, if you write this gives you the definition. What is 1 ampere? 1 ampere is defined as the current which flows in a conductor when 1 coulomb of charge passes through it in 1 second. Simple. This will give you the definition. You write this. 1 ampere of current is defined as the current which flows in a conductor through which 1 coulomb charge passes in 1 second. Very simple. So you have understood the unit also of electric current. Got it? Now how do we measure it? Okay, so for measuring current, we had done this in class 9 also. We connect an ammeter. Okay, we connect an ammeter in series. Okay, and the ammeter tells us how much current is flowing in the circuit. Simple. An ammeter is a device which is used to measure the amount of current flowing in the circuit, and it is always connected in series. And you must have seen I ensured that I have connected the positive of the ammeter to the positive terminal of the battery, and I have connected the negative to the negative terminal of the battery. Okay, that is a caution when you do practicals in your lab. There also you have to take this caution that you should always connect it in the proper direction. Clear, everybody? So 1 ampere is equal to 1 coulomb per second. We call it ampere. It is defined as the current flowing in a conductor when 1 coulomb charge flows through the conductor in 1 second. How do we measure electric current? We measure electric current using a ammeter. Okay, ammeter is always connected in series, ensuring that the positive end is connected to the positive of the battery, negative to the negative. That's it. Understood, everybody? Can we move on? Clear. Kritika says clear. Archika says clear. Okay, we move on. Okay. Now, if we have very weak currents, then what do we use? We use a smaller unit, again milliampere, microampere and nanoampere. दस नहीं नानो नहीं कर रहा, खाली मिली एंड माइक्रो. ओके, ये क्वेश्चन पूछते भी हैं कि हाउ मेनी एम्पियर्स इज 1 मिली एम्पियर इक्वल टू, तो इट इज़ 10 to the power -3 amperes and 1 microampere is equal to 10 to the power -6 amperes. सिंपल हो गया. आपकी बुक में केवल मिली एम्पियर एंड माइक्रो एम्पियर के बात कर रहे हैं. 1 मार्क क्वेश्चन में आता है हाउ मेनी एम्पियर्स इज 1 milliampere equal to, how many amperes is 1 microampere equal to. So you have to remember 10 to the power -3, 10 to the power -6. Okay, which means how much? Which means that 1 divided by 1000 amperes, and this means 1 divided by 1, 2, 3, 4, 5, 6 amperes. Got it? So if they are very small, really small currents, then we can measure them using the units milliampere and microampere. Next we go to flow of current. What is flow of current? Okay, how does actually current flow? Okay, now you have already studied in class 9 that there are conductors, then there are insulators, and then there are semiconductors. Okay, so what is the difference in these? That some of them behave like conductors, electric conductors, and on the other hand others behave like non-conductors. What exactly is the difference in them? Can somebody tell me? What is the difference between a conductor and a non-conductor? I mean, why does one behave like a electric conductor and the other doesn't conduct any electricity? What difference is in they make? quickly. Okay, I start till then. Now you see, there it comes. Shingarika conductors have free electrons, and very nice. We studied this. Shingarika is a smart girl. We studied this in class 9. Okay, so now we know that they are made up of atoms. There are millions of atoms inside them. Okay, in the conductor, the electrons in the outermost shell keep on moving out. Okay, and they keep on moving haphazardly. Okay, these are known as free electrons. They come in and go out, go into another atom, and it keeps on happening like this. These are known as free electrons. So if a substance has free electrons in it, then it behaves like a good conductor. Okay, it behaves like a good conductor. On the other hand, if something doesn't have free electrons, it behaves like a non-conductor. Okay, in electrolytes, now suppose it's not a conductor, it's electrolyte. Okay, then we know that we have got protons and cations and anions. Sorry, so we've got cations and anions inside these. Okay, so these cations and anions actually migrate, causing the electric current to flow inside electrolytes. Okay, and this we have already done, that if n electrons pass, then what is the total charge that has passed? That is Ne. Let's go on to the next one. There it is. Q is equal to Ne. This we have already discussed. Okay, so we can write current in terms of the number of electrons also. We can write it Ne by T also. Okay, that will be the total charge. N into E will give us the total charge that has passed. When I divide it by time, I get the current that has flown. And 6.25 also we have found out, this is the number of electrons which will make 1 coulomb charge. Got it? Which means that 6.25 into 10 to the power 18 electrons pass every second through the conductor. Okay, then 1 ampere current is flowing. Done? We move on to the next one. Now we go to potential. Now we have understood what is electric current, and we have understood how electric current flows. Okay, but why does electric current flow is the next question which comes to our mind. So we are now onto the concept of potential and potential difference. I'm sure all of you have understood the concept of charge and electric current. Kritika says conductors have electronic which keep moving. Okay, we talk about free electrons, Kritika. Yeah, we talk about free electrons. Okay, so if something has free electrons in it, it will behave like a conductor, and if it does not have free electrons, it will not behave like a conductor. Instead, it will behave like a non-conductor. Okay. So now we are on to the concept of, everybody understood the concept of charge and electricity? We go on to the understood. Very nice. Now, so we've got around 10 minutes more. We can start what is potential. Okay, and I'll start by taking the example of gravitational potential. Again, we have studied in class 9. Okay, that if why is current a scalar quantity, asks Amisha. Okay, can somebody tell us why is, which means she is, okay, why is it a scalar quantity? Tell me. Okay, we missed one thing. This question reminds me, we missed one thing. Okay. You know, when we studied electricity, when we started studying electricity, because we talk everything positive. Okay. So then we had found out which one should be called a positive charge. We named one positive and we named the other negative, right? And like we always do, we said that it is the positive charge which flows. Okay, we said that it is the positive charge which flows, and we started doing all further studies based on this concept. Okay, and this is known as the conventional direction. This is known as the conventional direction. Conventional means paramparagat. Okay, so parampara chali aa rahi hai. We say that it is the current is actually flowing, the positive charge is actually flowing. But when we discovered the atom, which was later, okay, when we discovered the atom, now we found out that what are you writing? Black? What do you mean by black? Achha, black is somebody's name. No, I'll tell you, okay. Now, so we had taken the direction of current to be positive, okay, that the positive current is flowing. But when we found out the structure of the atoms, we found out that the protons, that is the positive charge, is actually locked inside the nucleus, okay, and it cannot flow, Got it? So we now knew that it is the electrons which flow, okay. Now we know that it is the electrons which is, suppose this was A, this was B. So now we know that it is the electrons which are flowing in a direction from B to A, okay. So conventionally we still take the direction of current to be opposite to that of the actual flow of electrons. Clear? And now inside an electrolyte, okay, inside an electrolyte I have got anions, okay, and I have got cations, okay. I've got anions and I've got cations. Now both are migrating, okay. One migrate to the opposite end and the other migrate to the opposite end. Understood the reasons? Okay. In an electrolyte, both the anions as well as the cations will migrate, and they'll migrate in opposite directions. So here I cannot give them direction. Got it? Whenever you have a circuit, okay, you have a battery connected to it. We are studying potential. We'll study potential difference also. Okay, so create the potential difference. We have a battery connected to it. Okay. And inside the battery we have got electrolyte wherein the anions and the cations both are flowing in the opposite direction. Okay, so we cannot consider both of them. We take conventionally, we also know outside the electrons are flowing in the opposite direction, but we take the direction of current opposite to that conventionally. Got it? So direction doesn't have a role to play over here, right? Now, what is the concept of potential? Okay, first I wanted to do gravitational potential. Okay, now suppose this is the ground level. Okay, suppose this is the ground level, and I have an object lying over here. Okay, so this object is at 0 level. Got it? If I raise it, I do some work in raising it up to this height. Okay. So that work gets stored in it. Yeah, both the reasons, beta. I gave 2 reasons. Because of both these reasons we take current to be scalar. Okay. Now let's focus on this. We have got left with just 7 minutes. Let's at least understand potential. Okay. So this ground is the 0 level. Now if I do some work, okay, so that work gets stored in it. Okay, now this has potential energy. Okay, now this stone has potential energy, which means whatever work I did in it, it is stored in it. As soon as I leave it, it will start traveling towards the ground, and it will start gaining kinetic energy. Got it? Now similarly, we were studying only positive charges initially. So okay, so I say that I have a positively charged object. Okay, so it has its field. Okay, now I bring some charge from infinity. okay, and I bring some charge from infinity towards it. So as soon as it enters the field, what happens to it? It starts experiencing a force on it. Okay, why it starts experiencing a force on it? Because you can see that both the bodies are positively charged. Okay, which means now that if I move it further in, okay, then I will have to do quite some work, because I am doing it in a direction opposite to the force acting on it. The force is pushing it away, like charges repel, and I have to do, okay. So if I bring it to a point A, now whatever work was done to bring this charge from infinity to this point A, okay, that gets stored in it. Okay, so again similarly, as soon as I let it go, it will move out in this direction. Okay, so this is its potential. Let's read what's given in your book. We have read that like charges repel while the unlike charges attract each other. If a charge A is brought near another like charge B, okay, so I have a huge like charge, this one is B and this one is A, okay, so I'm bringing it close. Work has to be done in moving the charge A against the repulsive force, okay. So now like charges repel, so I have a force, repulsive force acting in that direction, so I have to do a work in, I have to apply force in opposite direction to bring it inside in this position. Okay. Similarly, if a charge A is brought near another unlike charge B, work is done by the attractive force on the charge A due to the unlike charge. Now suppose this was a negative charged body, okay, so it would again do work by pulling that object A towards itself. Okay, so in both the cases work is being done. In one case the force applied by the body opposite is attracting it, in the other it is repelling it, so I have to do a work to overcome that repulsive force. Okay, so some work is involved in moving charge in the vicinity of another charge. Therefore the potential at a point in a region of charge is measured in terms of work done. I have shown it to you in gravitational potential also. Whatever work we do, that work will get stored. Okay, so here also that work, whatever work we do in bringing the charge in, is stored, okay, in a moving test charge. Now A is our test charge, okay, from a point of zero potential. At infinity we take zero potential because there the field of the other body is not acting, so it's zero potential there. So from zero potential, when I bring it inside the field of the second body, I have to do some work, and this work gets stored, okay, as its potential. Since force between the two charges is zero at infinity, therefore we consider the potential to be zero. That I have already told you, at infinity there is no force acting, the field is not acting there, so there the force acting on the body is zero. Okay, so we have understood potential. Now let's look at the definition. What is potential? The potential at a point is defined as the amount of work done. Okay, now suppose its charge was n, okay, so whatever work was done, when I divide it by the number, that gives me the work done in bringing a unit charge. Okay, so the potential at a point is defined as the amount of work done per unit charge. Per unit charge in bringing a test charge from infinity to that point. Okay, it is denoted by capital V, and again it is a scalar quantity. Got it? Because the forces acting on it could be both repulsive or attractive. Clear everybody? So you have understood potential, and in the next class we will do potential difference, and we'll also do some numericals related to potential difference. Okay, Archika is telling she remembers my expression when I was actually explaining potential on the board, pushing it on the board, right Archika? Nice, you people remember it. That's why I do it all, so that my kids can remember it nicely. Okay, so that's all for today's class. Time is up. Thank you very much. Shingarika gives me a thumbs up. 8 of you are watching. Not even one has liked the video. Didn't like my teaching today? Please like the video before you sign off. Thank you very much, Archika. We'll do potential difference in the next class. Thank you. Bye-bye. See you.